My name is Connie Hassett. I'm a member of the Adult School Board and the Lecture Committee. Therefore, it's my extreme pleasure to introduce our speaker tonight, Professor Ali Yazdani, who is the third lecturer in this year, the 2012 series, Science Times, Exploring the Frontiers of Science. As a teenager in Iran, Professor Yazdani convinced his parents to send him to a class on the repair of black and white vacuum tube-based televisions. This was his first encounter with science and technology. After immigrating to the United States in the 1980s, Professor Yazdani studied physics, first at UC Berkeley, where he obtained his bachelor's degree, and then at Stanford, where he got his PhD. As a graduate student, Professor Yazdani became interested in superconductivity at very small levels. Bringing his expertise to IBM Almaden Research Center in California in the early 1990s, Professor Yazdani conducted the first experiments that probed superconductivity on the atomic scale with the scanning tunneling microscope. He showed how the response of a superconductor to atomic scale imperfections could illuminate the global phenomenon of superconductivity. He went on to establish research groups as a faculty member at the University of Illinois in the late 1990s, and then again here at Princeton in physics in 2005. Professor Yazdani's research program focuses on the development and application of novel experimental methods to directly visualize exotic electronic phenomena in solids. Through these studies, he and his group provide a microscopic perspective on many yet to be understood behaviors of electrons in solids. His research program expands experiments in many areas: high temperature superconductivity, magnetism in semiconductors, nanoscience, and the newly discovered topological phases of electrons. In each area, his research group has carried out important experiments combining the imaging of matter on the atomic scale with high precision spectroscopic measurements of electron behaviors in exotic materials. Professor Yazdani's research has been recognized by a number of awards and honors. He is a fellow for the American Physical Society. He has received an NSF Career Award and a Sloan Fellowship. He has delivered the Pagels Public Lecture in Aspen. He has been a Kavli Lecturer at Delft Institute of Science and Technology in the Netherlands. And in 2008, he was also listed in The Brilliant 10 by Popular Science magazine, which makes an annual list of the top 10 scientists under the age of 40. While he is no longer under 40, Professor Yazdani says he tries to fool himself into feeling fit by spending extravagantly on biking, skiing, and running gear. Professor Yazdani's talk this evening is titled High Temperature Superconductivity, Energy Efficiency Meets Quantum Mechanics. Please welcome Professor Yazdani.
Thank you very much, Steve. That was a very generous introduction. And thank you all for coming out this evening. I see we have almost a full house. So this evening I'm going to talk about superconductivity. Can we turn these lights off at the blackboard? First of all, let me tell you that this is actually close to a very special year to talk about superconductivity. Superconductivity actually turns 101 years this year. We had actually a big bash in 2011 celebrating the discovery of first superconductor by a Dutch scientist, Hayek Cameron-Owens. I'm going to tell you the story of this man and how he came about to discover superconductivity. And let me just, before we get started, let me tell you that superconductivity is a state of matter in which you have materials which can carry electricity without any resistance. Okay? So what is important about that is resistance basically means loss of energy. Okay? So before getting you to listen to superconductivity and why it's important and why it's interesting from a physicist's perspective, let me try to put this in the context of today, in terms of the context of technology having to do with our energy problem. So I'm going to start this talk by showing you a rather complicated diagram. Okay? This is a diagram put forward by the Department of Energy a few years ago. What you need to focus on is on this side, which is showing you where our energy comes from. Okay? At the very top, nuclear energy. At the bottom, petroleum and what we put in our cars. And what I want you to focus on is the width of these lines, which is the critical thing that I want you to take away from this diagram. So on this side is where the energy comes from, and on this end is where the energy goes. For example, in our homes, in our businesses, and in our cars. And what you notice is that there is a very big fat region here, which is called energy losses. Okay? And it's quite significant. Okay? So when we think about energy transport from where it's produced in a nuclear reactor or in coal plants or even by natural gases, we basically use the electrical network to bring this to our businesses and our homes. And there is a big part of that which can get lost. So how big is that? I'm sorry for this complicated diagram. So now let's think about the simple notion of electricity being generated in a factory, such as a nuclear power plant, and coming all the way to our home. If you actually put in the numbers, you find that about 10% of that energy is lost before it gets to our homes. Where is it gone? It's basically, it's in all the wiring, the copper wiring, which carries that electricity, which has electrical resistance. Okay? So this amounts to about 50 to 70 billion dollars a year. So it's a non-trivial amount of change. And not only that, nowadays we have the problem of having to deliver electricity in very densely populated areas. So it's speculated by 2050, 70% of humans will live in urban areas. Now imagine you try to deliver electricity to these urban areas, and you don't want to have these big, giant power lines over your home. Some places there is just simply no room, like for example in the middle of New York City. You cannot simply deliver electricity using the technology that we have today, looking ahead. So what we would like to have is a more efficient way of delivering electricity. We like to have less losses, and we like to deliver a lot of power. Okay, so how do we do that? So the story this evening is actually about a new class of superconductors, these materials that I'm going to tell you about, which has no electrical resistance, which could be useful for this purpose. And there was a major discovery made in our field about 25 years ago. I'm going to tell you this evening that superconductivity, mainly when it was discovered, was a phenomenon associated with things at very low temperatures. You had to cool things down very cold to get this superconductivity, to have no electrical resistance. But these fellows from IBM in the late 80s, they discovered that they could have this phenomenon in certain class of materials, which I'm going to tell you about, at the temperatures close to liquid nitrogen. Now, liquid nitrogen isn't exactly cheap, but it's not that expensive. And as I will show you this evening, it is possible to use these liquid nitrogen cooled superconductors to actually deliver quite a lot of power. Now, it's kind of interesting to go back to the late 80s and look at the cover of Time magazine when this discovery was first reported. And when you look at this cover of Time magazine, there is a picture of an electrical car, which looks rather fancy, and it's being plugged into the wall. And back then, this may have looked very futuristic, but today, this is where we're going. Essentially, we're going to have to plug our cars into the wall, and that's how we're going to power ourselves moving around. There is no denying it, that's what we're going to have to do. And this wall plug better have the capacity to basically handle all of our cars. Okay, so how do you do that? Okay, And this is where the story of superconductivity can actually play a major role. And it's already doing that. So those superconductors that were first discovered by those gentlemen at IBM are now beginning to come to the marketplace. In fact, these are manufactured by a company, American Superconductor, of a very similar material of those fellows. And it's starting to replace the regular copper wire that we use for delivery of power in our power lines. There are some examples of these pilot studies. For example, one not very far away from here, in Long Island. There is this strip of power which goes from New York City to Long Island. And you need to deliver a lot of power through a narrow area. And these superconducting wires are being cooled inside these tubes, and they are delivering quite a bit of electricity. There are now 3 major studies, or pilot studies around the United States. This is the one I just showed you, Long Island. Basically, those wires that I showed you inside those tubes are replacing what would have been looking something like that up above. And there is a similar study in Albany, which is delivering quite a lot of power. And there is one in Columbus, Ohio, which is actually at the level of a distribution, coming into the neighborhoods. So the Department of Energy is actually studying this technology and looking at whether this can take the place of copper wires at all levels of the electrical distributions. Now, before I get to the science, let me tell you one more thing which I find really astonishing. Just a couple of years ago, a South Korean consortium of electrical companies placed the order for 3 million meters of this wire that's going to basically revolutionize Seoul's electrical infrastructure. Okay? This is the same material, this high-temperature superconductor that was discovered by those fellows at IBM. Okay? Now, let me tell you a little secret. We have no idea how these materials superconduct. Okay? This is a major intellectual challenge for physicists. This is one of those biggest problems out there for us to understand how this phenomenon takes place. And I'm going to hopefully take you through the story to show you where this field comes from and why is it such an interesting problem. Now, it's not that this is probably not lost on you that if we could really push the temperature at which these things superconduct to higher temperatures and push their capacity to carry current, this is going to have a major impact on all of us. Okay. All right. So that was hopefully enough motivation for you to stay at least awake for the next half an hour. So that's why I think you should care about this subject. That's one of the reasons I care about it. So I'm going to take you back 100 years, and I'm going to tell you about a race about cooling things close to absolute zero temperature and how this led to discovery of superconductivity. I'm going to tell you about discovery of what I will call low temperature superconductivity. Superconductivity at low temperatures. And I'm going to tell you actually how we understand that phenomenon. And we understand it pretty well. I'm going to have to teach you a little quantum mechanics. I think we can do it. And then I'm going to tell you about the challenge with these new materials that are going to be everywhere, hopefully, and we don't understand the science. And lastly, hopefully I'll give you a glimpse of what we do, for example, in my laboratory to address this challenge and the prospect for the future. So let's start nice and easy. I think this is not going to scare too many people. We're all familiar with starting with gas and how we cool it down. Atoms and molecules basically become liquids. And then when you cool them further, you get yourself a solid, a periodic array of atoms that has rigidity. But what do we really mean by temperature? Okay? So let me take you back even further than 100 years ago and tell you the way Mr. Amonton thought about temperature. This is probably something my children learned in middle school, which is that basically if you think about a balloon and the pressure in the balloon, if you had a way of measuring the pressure of that balloon, Mr. Amonton made this following observation, which is that the pressure is proportional to the temperature of the gas inside. So you can make a following plot where you plot the pressure versus temperature. And as you observe this phenomenon, you observe that there is a linear line. Now you can obviously do the most simplest thing, which is to extrapolate this line to zero pressure. Okay? This is a very special point. This is a point where we call absolute zero temperature. You cannot cool anything beyond that. That's the coldest anything can get. Now on our everyday scale, that's minus 270 degrees centigrade. Okay? Scientists talk about degrees of Kelvin, and this is measured as the 0 degree of Kelvin, and everything about this is on an absolute scale, with that being an absolute zero temperature. Okay? So this is what we mean by absolute zero temperature. If you think about those gas molecules inside, basically they exert no pressure when you go to that absolute zero temperature. Okay? And this degree is named after Lord Kelvin, who basically first coined the term, although it goes back to Amonton to understand it. Now, the phenomena of, there was a race about the late 19th century, early 20th century, that all the scientists, chemists and physicists alike, were engaged in, which is to cool and liquefy all the known gases. Okay? And one of the major advances came from James Dewar, a Scottish physicist, a Scottish chemist, excuse me, who basically invented what we now call the silver flask. Okay? So this is a coated, it's a vacuum jacketed vessel which has silver coating, in which the radiation from the outside is reflected from this silver coating to keep the radiation out and keep what's inside cold relative to the outside. Okay? This is actually what looks like a simple, was a major advance in trying to liquefy gases and get to low temperatures. With this technology, he was able to liquefy hydrogen, okay, one of the lightest gas, and actually even make it solidify. And he could get to 14 degrees above absolute zero. Okay. Now, here comes our character in this story. He's the Dutch scientist from Leiden, Cameron Owens. And Cameron Owens is was a phenomenal scientist, and he had this motto, which is, I know there are some Dutch speakers in the audience, which I'm told it translates into knowledge through measurements. Okay, so he was an experimentalist. He wasn't a theorist, and he was one of these people who really first invented the idea of the scientific enterprise. Okay, what I mean by that is that he set up a laboratory. He was after this goal of reaching close to absolute zero temperature, and he was also going after the prize of liquefying the last gas that nobody else had liquefied, and that is helium. Okay, at the time where he set up his laboratory. So he set up a lab in Leiden with very sophisticated technology of his day, technicians and other scientists, and it was the first example of a large-scale laboratory aimed at a specific scientific question. So with this laboratory, he was able to liquefy helium for the first time. And he was able to get down to 4 degrees Kelvin, and then later to 2 degrees Kelvin, very close to absolute zero. And with this, he basically invented a whole field of physics, which we call today low temperature physics. Okay? And then, after basically reaching this level, he was able to ask the question, what happens to matter as you cool it close to absolute zero temperature? Okay. And the question he set out to answer is the question of what happens to electrons. Okay? So remember, electrons is what carry electricity in the wire. So let me just remind you, we have things that are insulating, that if you hook up to a battery and a light bulb, basically they don't turn on the light bulb. Okay? Things like diamond or plastics and even silicon at very low temperatures. Now, there are things like copper. And when you think about electrical conduction in copper, you think about the electrons basically hopping, if you like, between the atoms of copper to give you electrical conductivity. Okay? So Cameron Owen's question was, what happens to the electrical resistance of a piece of metal when you cool it down to very low temperatures? Okay? So I'm going to represent how well a wire carries electricity by how much it lights up a light bulb. Okay? So on this axis I have temperature, and on this axis I have the brightness of the light bulb. Now what happens is that if you take a piece of metal and cool it down, that light bulb becomes brighter and brighter as you cool the piece of metal down. The efficiency by which the electrons can carry electricity, even in a piece of copper, gets better and better as you cool it down. And the reason for that is that the electrons moving through the piece of copper bounce off of the vibration of the atoms, even in a piece of solid, and they get scattered. And as you cool the thing down, the atom's vibration calms down, and the electrons can flow better and better. Now, around the time where, we can represent this not just as a brightness, but as the electrical resistance that gets smaller and smaller as we cool it down. Now, around the time that Cameron Owens was basically asking this question, there was a deep theoretical question about what is the fate of electrons at absolute zero temperature. So there were differing points of view. Some thought, you know, electrons are kind of like atoms. As you cool the atoms down, they crystallize. So maybe they will freeze out, and your resistance will actually turn around and go up. Namely, your wire will carry less and less electricity as you cool it to close to absolute zero temperature. Some thought it would just saturate, it would just be some number. And some thought maybe it would just go smoothly close to zero. So the theory was not clear at all. And Cameron Owens was just set up to answer this question. This was really the question he was trying to answer. And the reason this is important at the time was that when you get close to absolute zero temperature, when none of the other things, none of the vibrations of atoms are important anymore, basically you're in the realm of quantum mechanics. Okay? You're in the realm at which, around this time, around the early 20th century, we were inventing ways to think about subatomic particles. And the question was, when you have none of that thermal agitation, what happens to those electrons? And this was a quantum mechanical question, which classical physicists didn't know how to think about. They would have just probably said it just freezes and just sits still. So Cameron and Owen basically built an apparatus specifically to answer this question. He used the ideas of Dewar. You see these many flasks. This is actually a diagram of his apparatus. And he made the startling discovery. And he made this discovery using measurement of electrical resistance of mercury. Okay, so remember, I showed you the light bulb, and the resistance is basically telling you how well the light bulb is lighting up. The resistance was some number. These are his data points. He cooled it down, and at some temperature, the resistance dropped, and it went to zero suddenly. Nobody had thought that would happen. Okay, so this was a complete surprise. Okay. Now, he made the announcement of this discovery actually in one of the most important meetings in all the history of physics. It's actually kind of startling to go back and look at the picture from the people who attended this meeting. You recognize some of these people, I bet. There's Albert Einstein, okay? And there's Madame Curie. And those of you who are familiar with you can probably name a few other people in this group. And there is our man, Cameron Owens. And why is that man smiling? He's smiling because a few years after this announcement, he basically won the Nobel Prize for not only liquefying helium, but giving birth to this whole field and discovering superconductivity. It turns out that he discovered another very important thing. Something those of us who have a sports accident use all the time. So let me tell you about that one. So he made discoveries of many superconductors, mostly elemental things like mercury, thallium, cadmium, didn't superconduct, lead. But if the resistance is zero, if you make a little loop of the superconductor, what that means is that if you inject an electrical current, the current can go around this loop forever. Okay? So he actually made a little coil, and he made a very ingenious switch, which I won't get into how he did that. He injected current through this coil, and then basically this switch was made out of a superconductor that was raised above this transition temperature, then cooled down to close the loop. And he basically showed that this current running around, producing a magnetic field, which is what currents do when they go around in a loop, this magnetic field basically stays on forever. In fact, there's been studies to try to measure how does this current decay. The rate of decay is very slow. Basically, we're talking longer than the age of the universe. Okay? If you keep the thing cold enough. And this is not what happens in many other things that we think of constant. Like when we think of a satellite going around the Earth, it could dissipate and it could lose its orbit. So this is a very special phenomenon when you think about something going around forever. Okay? So those of us who have had accidents have been in Cameron-Owens loop. This is basically how an MRI machine works. The magnetic field that's used for this imaging technology is used using superconducting wires. And inside this ugly-looking thing that we all hate because it makes a lot of noise, there is superconducting wire going around that's cooled to liquid helium temperature. And it gives us images like this one of your ripped ligaments and so on. It's also used, the magnets are also used in particle accelerators. My colleagues who study what subatomic particles are made out of use to accelerate particles close to the speed of light and smash them together. Okay, so this is a technology that's basically everywhere. Okay? There is another special property of superconductors, which I'll hopefully show you a movie at the end. They actually...
It's 8:30.
I'm sorry. It's my computer. So there is another special property of superconductors, which is that they expel magnetic fields. Okay? And this is something that comes about because of this, if you want to think about these currents that are flowing inside the superconductor, expelling a magnetic field. And it's actually being used to make magnetically levitated trains. I'll show you some pictures of that at the end. Okay, so superconductivity was discovered, but how does it work? Okay, and then we'll get to the puzzle of high temperature superconductivity. So to do an attempt at explaining this phenomenon to you, I need to take a slight detour. I'm going to have to explain a few things about quantum mechanics to you. I'm going to have to try to explain quantum superposition and entanglement. Okay? So let's go back and think about waves. Okay? Water waves, sound waves. Some of you may have heard of the phenomenon of interference. Okay? So imagine you have sound waves or water waves impinging on basically two slits. Okay? Now what happens here is that as this wave goes through these two slits, you can think about waves emanating from each of those slits. It basically interferes on the back side, and if you put a measurement on the very far side to look at how the waves arrived at this far end, they give you an interference pattern like the one that's shown like this. Okay? So this is basically what you get on a pond if you throw rocks and watch the waves basically interfere with one another. Okay? This is a special example of that, but it's nothing that unusual. But what's unusual is when you think about quantum mechanics and subatomic particles, like electrons. Quantum mechanics tells us that subatomic particles not only behave like particles, but they can behave like waves. What does that mean? What that means is that if you made the same experiment using a sprayer of, let's say, electrons, and you made your two slits, and on the back side you measure the arrival time of electrons on the back side of this, and you did this many, many times, you basically get the same kind of interference pattern you would have had for waves. Okay? How is that possible? Well, This is one of those things that's very unusual. It's very hard to come to grips with. Electrons can be both a particle and a wave, but this really works. For example, if you do an experiment like this and actually find a way to try to look which slit did the electron go through, you basically destroy this interference pattern altogether. This is one of those things where if you observe it, you disturb it in quantum mechanics. Okay? But this is a very real phenomenon which has been tested through and through for over 100 years. Okay. Now, let me make this a little bit sophisticated. Let's just think about the two ways in which the electron can go through one little equation in this talk. One symbol L representing the particles going through the left, one symbol R representing the particle going to the right. So basically what the quantum mechanics tells us is that you have to actually think about the superposition of the particle going through both paths to the other side. Okay? With me so far? Good. So now, let's not think about two slits. Let's think about lots of slits. Now let's think about lots of positions as opposed to slits. So imagine that each side is like a path through the slit. And I have just one particle, one subatomic particle. And basically what the rules of quantum mechanics tells me is that I can think about this particle not only just being here, but here, 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 everywhere, if you like, with equal probability. So I think about that as a superposition of all the possibilities in which this particle can be, if you like, everywhere. If you think about the seats in this room, that particle can be in every seat. Okay? With me so far? Now let's make it more complicated. Let's not think about one particle. Let's think about more than one particle. Like all of you in this room. And imagine that I want to make an entangled state, which is only possible if you are all subatomic particles. And you could be in every seat in this room at the same time. Okay? That's pretty weird, right? So let's just be specific. So if you had 3 particles, 3 sides, you can think about 27 possibilities. Okay, that's manageable. But when you think about electrons moving inside a piece of solid with those many atoms, you think about 10 to the 23 electrons. Okay? And think about those 10 to the 23 electrons being at every location, not electrons, let's just say subatomic particles, that can be at every location at the same time. Okay? So this is a very special, what we call quantum fluid. Okay? And it turns out this is what a superconductor is. It's a fluid of highly entangled quantum particles, which can be in every place, if you like, at the same time. Okay? And if they're everywhere, if you like, that's a state in which you have no electrical resistance. Okay? So this state is actually called a Bose-Einstein condensate. It's named after an Indian physicist named Bose, who first proposed the idea to Einstein. And Einstein said, yeah, I think you're right. And he extended the idea, and they both published at the same time, I guess. And what I want you to focus on is that there is this quantum superposition of many particles, okay, in many locations all at the same time. Okay. And now it turns out what the superconductor is such an entangled quantum state, but not of single electrons. It turns out, for reasons that I can get into details, but I won't, single electrons can't do it alone. They need to have pairs. There needs to be a pair of electrons. Okay? It's a difference between what's called a type of particle called a fermion and a boson in physics. And it turns out that electron is called a fermion, and fermions can't do what I just showed you, but bosons can do that. And a pair of electrons makes a boson. Okay. But wait a minute. But electrons repel one another, right? So how do they make pairs? Okay, so this is a puzzle that goes back to 50 years ago. Actually, physicists realized that if you find a way in which you can make electrons pairs, then you can make that superconducting state using the ideas of Bose and Einstein through the diagrams that I try to explain to you. Okay, so it's really as straightforward as that 50 years ago. So, but electrons repel one another. They fly apart, we think. But not quite. So I'm going to remind you about your, I think, middle school now. You're now up to middle school. Middle school chemistry. Remember those electrons inside the atom? Okay, so here's your nucleus. Your electrons are going around in your Bohr model that we all learned and love as middle school children. Remember all these electrons? They're not flying apart anywhere, right? They are attracted to the nucleus. But remember how you had to color in and make shells and put so many electrons inside each of those shells? Those actually, you are following rules of quantum mechanics to do that. Okay, you just didn't know it. They told you it was chemistry, but it's really quantum mechanics. That's okay. But the key point here is that we're actually comfortable with the idea that electrons repel one another inside an atom because we think about their repulsion being tamed by the fact that they are attracted to the nucleus, and also the fact that when they fill up these filled shells, basically there's no room for them to do anything. They can't go anywhere. It's a filled shell. Okay. So it turns out that inside a solid, a very similar thing happens. Okay? You don't have one atom, you have many atoms. You don't have one electron shell, you have many electron shell. But the electrons, they're the levels, just like those quantized levels of a Bohr atom, those little shell model that I described. You can put electrons into them, and once you fill them up, they become irrelevant, and you don't have to think about them anymore. Okay? Remember, all the chemical activity of an atom was related to what happens to the last electrons in the shell. So it turns out that if you take a piece of solid, okay, regular sort of simple solid like a piece of copper, you can think about the electrons when they're cold as essentially free particles, okay, even though they repel one another. And you can get there by thinking about it in the way of filling these levels. The ones that are filled are irrelevant, and the ones that are not filled are almost like non-interact. They don't repel one another. And the person who actually first proposed this idea and showed that it was true was a Russian physicist by the name of Lev Landau, who won the Nobel Prize for this idea. Now, so our notion of electrons in solid is now sort of more sophisticated. Electrons are almost free. They don't repel one another as vigorously as we think about. But how do they attract one another to make a pair? And this was actually one of those big milestones in the field of superconductivity, which basically blew the problem wide open. Basically showed us that once you make the pair, you're all done. You can get the phenomena of superconductivity. And the discovery was made by 3 American scientists, which showed us that the electrons can actually attract one another under certain conditions by the way in which they interact with the lattice through which they move. Okay? So I want to use the analogy of a waterbed. You can get 2 people who really dislike one another. You can put one on the waterbed, and they will make a little sort of depression, if you like. If you put the second one on the waterbed, they're very likely to roll over and be next to the person that they were there before. So you can think about electrons moving through the lattice that's mostly positively charged background of ions. And if the ions basically are a little displaced, if you like, it's like an extra positive charge, if you like. Electrons are attracted to that site. And the second electron, if this electron could be long gone, the second electron can also get attracted to that site. So these American scientists basically showed us that there is a way in which you can get electrons to actually like one another, which is very bizarre. When they move through a crystal, and once you make them paired up like this, quantum mechanics take care of the rest. They will make them into that entangled state that they can be at all locations at the same time, and you get yourself a superconductor. So the discovery by these American scientists earned them a Nobel Prize in the 1970s. And basically, between 1970 and 1980s, this superconductivity became a very well understood field. It was very successful theory. And it explained basically all the superconductors that Campbell and Owens discovered, and many, many people discovered throughout the 1970s and early 80s. And basically, the whole field focused on the idea of how can you get higher temperature superconductors. Okay? So the superconductivity, as I will show you in a minute, was basically limited to like a few tens of degrees above liquid helium. It hadn't advanced in terms of material very far from those early days of the 20th century. So the field focused on search for new materials. How can we find new superconductors? And right here in New Jersey, not very far from Princeton, was one of the key places where people looked for superconductors. Some of you, I'm sure, remember Bell Labs. And Bell Laboratories basically knows not only some place where the laser was discovered, but much of the research in the field of solids and superconductors was being carried out at Bell Labs. And one of the key characters was a fellow named Bert Matisse. Now, Bert Matisse was a chemist, and he really had a good feeling about materials. And you can imagine that the periodic table is very large, and you can make a lot of combinations. So there is a world of compounds you can make out there and look for them to be superconducting. Now, the story of high-temperature superconductivity is interesting from the perspective of thinking about what work was going on in the 50s all the way to the 80s, which is that most scientists basically followed rules that was set up by Bert Matisse for looking for new superconductors, because he was so successful in finding them. He would find like a new one every few months. So he had these rules. Look for symmetric lattice structures. Avoid oxygen. Anything oxygen in it, forget it. Avoid anything that could be magnetic. Magnetic, superconductivity, they don't like one of them. Avoid insulators, obviously, but avoid materials that could be close to being insulated. Most important of all, don't listen to the theorists. These were his rules. And he made a living following these rules and really trained like generation of American scientists who discovered one superconductor after another and really pushed the field wide open. But something unusual happened in the 1980s. So the progress that I told you about following Matthias' rule basically limited us down here. So this is temperature, this is year, and basically going up to like early 80s, essentially we were down at liquid hydrogen, very cold. You know, well below the surface of Pluto in terms of temperature. And these IBM scientists that I told you about at the very beginning basically made the discovery that led to this huge jump in the temperature, going from superconductors that were superconducting on the temperatures equivalent to surface of Pluto, well beyond nighttime on the moon. Liquid nitrogen is right here at 77 Kelvin. Okay, that's a critical number. And nowadays we are up to 165 Kelvin, which is actually off this chart. Okay. So these guys really made an enormous contribution. How did they do it? This is their discovery led to hundreds of compounds that are high temperature superconductors. These are just some examples of the lattice structures. But did they follow Matthias' rules? Symmetric lattice? No, they didn't do that. They ignored that. Avoid oxygen? No, these are all oxides. You see they have oxygen in all of them? They're almost magnetic. Okay? And what's interesting is that if you adjust the electron content, the number of atoms in this compound just a little bit, they become insulators. The only thing they did do, which is that they didn't listen to the theorists. And their discovery led to this enormous number of compounds. Now, it turns out that all these compounds have something in common with one another. They all contain something extremely beautiful and simple. They contain a lattice of copper and oxygen atoms in a square lattice. Okay, all those complicated lattice structure stuff, you can forget about it. This is it. Okay, this is a lattice, and this is a rendition of artist's rendition, my student's rendition of what the most important atomic orbitals are for this particular lattice of electrons moving in this particular lattice is where superconductivity comes in. It has copper d orbitals, which are these attractive-looking clover leaves, and it has oxygen p orbitals, which are these dumbbell-looking objects. Okay. So it's extremely simple. So why is this such a hard problem, right? Well, let me go back to the beginning, what I just described to you about how the old-fashioned superconductors work. Remember, I told you electrons almost move freely in a piece of copper or a piece of aluminum, actually, that goes superconducting. And I told you about the lattice mediating mechanism, which the electrons attract one another, make this quantum superposition of state, and they become paired and entangled. This happens at very low temperatures. New superconductors, high temperature superconductors. Yes, there are electron pairs in them. We know this for a fact. I won't tell you how we know experimentally. They can get up to superconducting to much higher temperature. Like these are highest TC 20 Kelvin above absolute zero. This is 160 degrees above absolute zero. Okay? Now, here's the thing that's really hard to understand. It actually turns out the superconducting state is one in which we have a handle on, but we don't know what the electrons are doing when they're not superconducting. Okay, so you might think, why is that important? Well, it turns out that's really important because if you don't understand that, you can't figure out how they went superconducting. Okay, so the phenomenology is is evolving, is making progress. But now we understand that to understand what happens at very low temperatures when the electrons make this quantum state that carry electricity without any resistance, we have to go back and understand what they're doing up here at high temperature. It turns out that they don't behave like free particles. Okay? So you might think that's very complicated. It's actually quite simple. So let me try to explain it to you. So remember, I told you that you can be an electron, and in order to get electrical conductivity, you have to hop from place to place to place. So imagine people in this room, if they all really like one another, and they don't mind all of them, several of them being in the same seat, we can get a lot of people conduction here, right? You can get electrons moving around. And remember, I told you if you can overcome electrons disliking one another, that's how basically things happen in a simple method. Now, in these materials, in this very important plane, which has copper and oxygen, if you think about electrons moving around, electrons basically have to go through these little orbitals, which has these good-looking clover-leaf shape. These are d orbitals. It turns out you can't put two of them at the same location. It just costs too much energy. Electrons cannot go on the same place. Okay? It has to do with the fact that this discrete lattice, these electrons have to go onto this very tight space of this atomic orbital, and they don't like to go there. So now imagine that I tell you that we're going to fill this room with people and just have a few people missing. Okay? And now we want to get people conduction. We want people going from place to place, but having to also always sit in a seat. They can't just be standing up. You see, that's very hard to do because you have to find a seat where there is not another person. And if there's a lot of people in a room, that's just really correlated and difficult. And this is the essence of this problem. The electrons, when they are not superconducting, they are in this traffic jam in which they're all in this lattice, and they have to kind of avoid one another to go from place to place. Once you make a few little absent electron sites, you cool the thing down, and boom, it goes superconducting. And that is what we don't understand. Okay? So this is really, I've brought you really, I hope, to the frontier of what the key question is in this field. Is how do you understand this collective state of electrons on this lattice, and how do you, when you cool them down, become superconducting? So I have 5 minutes. How am I doing time-wise? Okay, it's 8:51, so I have 10 minutes. So I will take a few minutes to tell you, for example, what are the experiments like we do in my laboratory to answer this question, for example. So just to give you a flavor for what the frontier of this field looks like. So in my lab, we've developed the tools in which we can actually look inside the material and watch electrons, if you like, and take images of the electrons as they move through the solid. Okay? And we do this using something called the scanning tunneling microscope. It's kind of like a, if you like, it's like a photograph. you have a very sharp tip, which you bring near the sample, but you don't touch the sample. Okay? You put a electric field across this by connecting, if you like, a battery between your sample and the tip. The tip is conducting. And even when you're not touching the sample, if it's close enough, the electrons can, what we call, quantum mechanically tunnel between the sample and the tip. Okay? This is a quantum mechanical phenomenon that doesn't happen for big particles. It happens with subatomic particles. They go across this gap, even though they're not allowed to be in that gap. Now, once you have this tunneling happen, you can actually take this tip and raster it around the surface and sense where the electrons are underneath your tip. Okay? This microscope was actually incidentally invented. The very first one was actually built in the same lab in which high temperature superconductivity was discovered. There's something special about this IBM lab in Zurich. Now with this instrument, what we can do is we can basically take an image of where the electrons are. So for example, if you do this on a simple metal, let's say platinum. Okay, platinum is not exactly blue. But what you do is you take this current that you measure from the microscope, and that signal you can false color to make an image of how that current basically changes as you move raster that tip very precisely around the surface. So you can go down and really image single atoms with this instrument. Okay? And here is an example of imaging a high temperature superconductor. So let me try to set the scale for you here. This is an image which is 65 nanometer by 65 nanometer. 1 nanometer is 1 billionth of a meter. Okay? And what we're really zooming in is zooming in on individual atoms. We always knew atoms existed since the invention of X-rays, but it really took this type of instrument to really see them. Okay? But also actually move them individually. But I'm not going to talk about that. So here is a patch of microscopic landscape in which electrons become superconducting at very high temperatures. Okay? So now, this is not quite a picnic doing these experiments. It's a kind of a bad marriage between low temperature physics that Campbell and Owen invented, ultra high vacuum, you have to have very clean surfaces to do these experiments, and very low vibrations, because the shaking of the tip relative to the sample will blur your pictures. Okay? So people who work in this field, like us, have kind of a bunker mentality. They put their instrument inside a bunker, deep on the ground, build walls around it, and isolate it from the environment. Okay, so with this instrument, we can actually interrogate a superconductor in ways that was not possible before. So remember I told you that superconductivity involves pairs of electrons. Electrons that attracted one another, they made a pair, then they became this collective state in which they became very entangled. So when we bring this tip, we can basically rip them apart. We can try to suck electrons out of the sample by ripping those pairs apart. So we have a kind of a sensor. Okay? This sensor, basically if you have no electrons paired, the current can flow between the tip and the sample. You get one kind of signal. If they're weakly paired together, they don't like to get out of the sample, the current will get smaller. But if they're very strongly bound together, these pairs are really strong, which makes a very good superconductor. Basically, the current will be even smaller. Okay? So just to give you a flavor of the kind of things we do, we take this microscope and we actually have been able to image where these pairs are inside the crystal of this material. And one thing we have found that's very surprising is that actually where the pairs are, the color scale here represents the strength of these pairing of electrons, the red being very strong and blue being very weak, as measured by this microscope. And this is the same landscape over which you have this picture of the atoms. This measurement tells you where the pairs are stronger and weaker, and this measurement tells you where the atoms are. Okay? So you already see something very interesting. Over here we have a red spot where the electrons are paired very strongly. Okay? So my theoretical colleagues are very interested in this because they wonder whether if you could make a material that's equivalent to this red spot, that could end up being a very high temperature superconductor. Whereas you want to avoid the blue spot where the pairing is weak. In fact, you can do experiments where you can watch these pairs go away as you warm the sample up. So this movie here is actually visualizing this process by which you see the pairs, the colors red being very strongly paired, and white being basically not paired at all. And we can actually take a picture of this atomic landscape and ask questions, detailed questions, about how these pairs are moving on. Okay, so these are the kind of things we're learning. And it turns out that these type of tools are really critical to answer this question. For example, right away from these experiments, we have learned that whatever is the mechanism in which you make these electron pairs, that mechanism is extremely local. You just need like a patch of atomic landscape of maybe 5 or 10 lattice squares of that special copper oxygen plane to nucleate this special state. Okay, so let me conclude. Where is this field going? It's going in many different directions. It's inspiring a lot of different type of work. But one thing is for sure, if we're going to make progress in terms of making materials that really go into, for example, power grid network, material discovery is key. And unfortunately, a lot of this is through serendipity. Okay? The theoretical sort of approaches that we have, while they can be used as a guide, they're not predictable enough to basically drive us to a place where we'll look at this material, we'll look at that. A combination of synthesis and looking at theories is very critical. But since the theory, as I showed you, is in a very bad state right now, because that traffic jam of electrons on a lattice cannot be solved on the world's biggest supercomputer even today. Okay, it's very difficult. New experimental approaches, I showed you one of them. New theoretical approaches. In fact, what's interesting, well, let me just tell you one thing. For example,
It's 9 o'clock.
You can blame my children. Okay, so for example, new materials. Just a few years ago, a new class of materials were discovered that were based on iron to superconduct at very high temperatures. Remember those rules with magnetism? You know, rules are meant to be broken. In terms of new theoretical approaches, actually, what's interesting is that my colleagues who spend their time worrying about subatomic particles and unifying theories of subatomic particles and gravity, which, for example, work in string theory, like Steve Butzer, are actually applying some of the mathematical power of string theory to try to understand what happens for these highly correlated states of electrons. So there is a lot of crossover also into other parts of physics which you would have not thought about being relevant. So now to conclude, I think the ultimate question is, can we have a room temperature superconductor? Right? Because that would change everything. And so you guys have been a great audience and very patient. So I thought I'd end this by telling you that Hollywood thinks that a room temperature superconductor is certainly possible. In fact, there was this movie. I don't know if any of the people in this audience seen this movie. And there was this thing called unobtainium, which is basically a room temperature superconductor. Okay? And if I can get this to work, I'm going to show you a little movie, which is there we go, which I found very amusing.
I love this putter, Ronnie. I love this putter.
Parker, you know, I used to think it was benign neglect, but...
All right, let's see if we can make it work over here. can see what I'm doing. Oh, here, just push play. Sorry about this.
Now I see that you're intentionally screwing me.
Grace, you know, I enjoy our little talks.
Sorry.
Oops. I need a researcher, not some jarhead dropout.
Well, actually, I thought we got lucky with him.
Lucky?
Yeah.
How is this in any way lucky?
Well, lucky your guy had a twin brother, and lucky that brother wasn't some oral hygienist or something. A Marine we could use. I'm assigning him to your team as security escort.
The last thing I need is another trigger-happy jarhead now.
Look, you're supposed to be winning the hearts and the minds of the natives. Isn't that the whole point of your little puppet show? You look like them and you talk like them and they'll start trusting us. We build them a school, we teach them English, but after what, how many years? Relations with the indigenous are only getting
Yeah,
worse.
that tends to happen when you use machine guns on them.
Right. Come here. This is why we're here. Unobtainium. Because this little gray rock sells for 20 million a kilo. That's the only reason. It's what pays for the whole party. It's what pays for your science. Comprendo? Now those savages are threatening our whole operation. We're on the brink of war, and you're supposed to be finding a diplomatic solution. So use what you've got and get me some results.
Okay, so I hope that if room temperature superconductor is found, it's found in a laboratory, not in some faraway land. So, thank you very much. Go ahead.
So you mentioned toward the beginning that observing the slit experiment causes the interference pattern to go away.
That's right. So if you look to see which slit the particles went through, the whole interference pattern is destroyed. So the whole notion of interference, it's there if you do not make a measurement of which path the particle took. And this is a key part of quantum mechanics, where the interference is possible, and this has been demonstrated experimentally.
And does that have any implications for observing the superconductor with the scanning tunneling microscope?
Oh, that's a good question. I think the way you think about the tunneling microscope is basically you have, you're not observing a specific particle. You're making an average measurement, which is very, very slow. And you're basically, it's kind of like the screen in the back, if you like. It's a very slow process. You're measuring basically 1 electron every nanosecond, which may sound fast, but on the scale of electrons moving around inside the solid, that's about 1,000 times slower than when the electrons rearrange themselves.
I read a lot of science fiction. Avatar was the next movie. And you never know whether the people writing these are doing good science or not. But a lot of the things that they portray is, for instance, they take say, a car battery today. If it ran through superconductor material, how much longer would that battery last?
Oh, that's a good question. Okay, I think in terms of the car battery, that probably wouldn't make any difference. Because basically what you want the car battery to do for you is turn the wheels, which is basically a dissipated process to begin with. So that you wouldn't want to put superconducting wires in your car. That wouldn't really help you that much. But if you put superconducting wires where you need to push a lot of power to Long Island in a small little area, then it makes sense. Because you are both constrained in terms of space and both constrained in terms of how much power you want to push through. And you don't want to have, you don't want to build crazy infrastructure to do that. So that's where this type of technology could have a huge impact.
So it lower the cost of electricity to the consumer.
Well, basically, if you can recoup that 10%, and that's a big deal. It's $50 million, $50 billion.
What about graphene? Doesn't that allow electrons to go without resistance? You just can't shut it off.
So what she's talking about is a new discovery of the fact that you can basically make an atomic layer of carbon atoms, which is called graphene, and you can isolate this atomic layer. And graphene probably will have its application in transistor technology more than power technology, because of the ways in which you can control electrons on it. The speed at which the electrons will move on it would really contribute to turning on and off your transistor much faster. That's probably where it would be most useful.
In the case of the Long Island distribution power, if you lost coolant, what did you get? Instant frying system?
That's a good question. I think the answer is yes. So, but it's not quite as bad because the way they're doing these wires, I showed a picture of it. They're using silver as one of its core. I think maybe it's some compound that has silver in it. So you might fry the superconductor, but it's not like you won't be able to deliver the power. So you might have to replace some of the wire. Yeah. It wouldn't be as good as it was before, but it's not like it's just going to create a huge fire. So they're using quite a bit of silver, and the superconductor is kind of shorting out the silver. If that makes sense. But there's a lot of technology that's going into making up that wire. They're making these in tapes, and they lay them over each other. It's quite complicated.
How do they actually cool the water?
They literally, so there are many different technologies, but the ones I showed you, they're really literally running liquid nitrogen through there, okay? Or keeping, so it's like a jacketed tube, which is isolated from the outside world. And you can make those very efficient. For example, just to give you a feeling for this, in an MRI machine, they put helium into it once a month. You never see anybody coming in there while you're going to the hospital putting liquid helium into it. So you can design the systems very efficiently. And if you could push the temperature higher, you could use what's called thermoelectric coolers, which is the same electricity that you generate can be used to cool your wire. So those can be more efficient. Sorry. Those can be more efficient than using like liquid nitrogen. Go ahead.
How expensive is the infrastructure? Specifically, 10% still have to pay for it.
Yes, excellent question. So I think that the cost is in the wire. Yes. No. The superconducting material. So for example, the one that's being used, it has bismuth, strontium, calcium. So these are elements that are expensive. So that's another frontier. Make it cheap. Not of these materials, but using other materials that could be more earth abundant, or simpler crystal structures, or cheaper to make. Go ahead, I don't think.
In your superconducting materials, you showed that there were islands of higher temperatures and lower temperature thresholds. Do you see any correlation with your STEMs on what's different between one area and another?
So that's a $640,000 question. So we see a lot of correlations with different quantities. For example, it turns out these materials, in order to make it superconducting, you start with that beautiful plane that I showed you, but you have to adjust the chemical structure of the other planes in order to make it go superconducting. And when you adjust the chemical composition of the other planes, that produces a heterogeneity in the material that this microscope picks up very well. And correlating that information with the local strength of the superconductivity is the thing that's very important, precisely. I mean, there's no simple answer I can give you, but otherwise I wouldn't be here talking. The problem would be solved, right? I think we have.
So these long-distance wires, like I want, have to be.
They're not actually. That one is not very long. It's just a lot of power being pushed through. Yeah.
But it has to be enclosed into.
Yes.
That keeps
coolant.
Coolant. And so wouldn't it be susceptible to anything functionally about fighting it?
No. These are basically metal, casing. The pictures I showed you, as far as I understand, it's not.
It's not like it was just dragged out.
No. It's a very well-designed system where you have you can push the liquid nitrogen through, it won't leak out. It's not, but it's not that makes sense for very long distances, right? Because you have to cool a big chunk of wire over very long distances. I think where it would make a big difference is very delivery of large amount of power in urban areas.
Maybe one more question or two.
I think I found one.
In your new superconductors that you work on in the lab, there must be a lot of difficulty in keeping them very pure. Is purity an issue in terms of what happens in the superconductor?
So it turns out that one of the challenges with the new superconductors is they are not what we call stoichiometric. They're not like elements like niobium, lead, which are very simple elements that you can purify. So there is quite a bit of work that chemists and physicists do to isolate the right compound, which has the highest temperature, superconducting transition temperature, or the right property. Yes, it's all about making the right sample. That's what it's all about. And once you get the right sample, you isolate the phase that's sort of the best. This is what drives the field. Yes, there's quite a lot of work in trying to do that.
Are the cables that are being used susceptible to vibrations?
No.
So there's no exterior force that would have an impact?
I think the main question is the materials in terms of where is the cost-benefit analysis makes sense for you to start investing in this kind of technology in terms of buying the wire. Apparently the Koreans have crossed that threshold. There is some, obviously, infrastructure associated with the coolant, which is, I think this is all evolving as a function of time. But I think it really comes down to, when does it make economic sense? And it's starting to.
There's no such thing as a squirrel eating the insulation and taking out.
I don't think that's an issue here. No, I mean, unless your squirrel can withstand cryogenic temperatures.